what is the probability of a random, I wish I could type on this, selected student at CMCC has a GPA of 2.7. GPAs follow a normal distribution. GPAs follow a normal distribution with, so I take my whole whiteboard just to write the problem out, with a mean of 3.0 and a deviation of 1.2.
Tonic thinking. Holy smokes. Woman as the Puminala. Yeah? I left it. Stop. No, I'm just telling you that what I'm talking about. Okay, just
Make sure you guys mute your thing. I got everybody muted, but it says we still can hear stuff, so I don't know why it's not working. There it goes. All right, what is the probability of randomly selected a student at CMCC has a GPA of 2.7? GPAs follow a normal distribution with a mean of 3.0 and a deviation of 1.2. So this would be very similar to how our problem is on the test, as well as the homework, right? So a couple keywords just so we can understand what we're going through here. All right, it has a normal distribution with a mean of 3.0 and a deviation of 1.2. So if I put symbols to this, this is your mu, and this is your sigma. And then we are looking for the probability of a randomly selected a student at CMC who has a GPA of 2.7. So this is our event, which is our X.
Is that a blinker?
Yeah, I'm trying to mute right now. All right. So we got our X, we have our mu, and we have our sigma, right? So let me go to a new screen here. Step one, we always draw our picture, right? And since the problem said it's normally distributed, excuse me, we draw a bell curve.
Bless you.
Right? Thank you. This is step one. And our bell curve is always centered at our mean, mu, which in this case we said was 3.0, with a deviation, which I like to write over here, of, I forgot, 1.2. 1.2, right? And we are looking for the probability that my GPA is, was it less than? Less than, let's go back and make sure I'm doing this. GPA 2.7 or less. And then write the or less in there. B is less than 2.7. So if 3.0 is in the center, 2.7 is right there. Draw our line up. And which way do we color?
To the left.
To the left. So last class, we were doing stuff that was centered always at 0 with a deviation of 1. We are no longer centered at 0 with a deviation of 1, which is typically what happens in a lot of real world applications, right? So step 1, we still draw our picture. Step 2, we now find our z-score. So remember, z equals x minus mu all over sigma. Again, I recommend you add parentheses. So then we get 2.7 minus 3.0 as a subtraction, all over 1.2. And what do we get? Negative 0.25.
Yes.
Good. So then our third step is we do what?
Follow the chart.
Follow the chart. So our z is negative, so that means we are on the negative side. So then we go find first, we find the first two numbers, right? So we'll put a little dash in here. On the left column, find negative 0.2. And then go over to 0.05. And if we do that correctly, we get an answer of 0.4013.
I'm sorry, could you like explain the chart again? Like
Yep.
how you do it?
Yep. So if you're looking at your chart right now, we have a negative z-score, right?
Yeah.
Is that right there? So go to the negative side, and the far left column has a little z on the very top.
Yeah.
So then you go through that column and you find negative 0.2, which is almost to the very bottom.
Okay. And then over 0.5.
Then you go, then you
0.5.
line it up. Yep.
Point.
Then you find the 0.05 on the very top. Drag that finger down, drag the other finger over. And when the two fingers line up, which should be at 0.4013, that is your answer.
All right. Cool. Thank you.
Yep.
Let's
So
go.
therefore, there is 40.13% chance that a randomly selected student at CM has a GPA of 2.7 or less. If the GPA at CM is 3.0 with a 1.2 standard deviation. I don't know if it is or not. I made that up. So not much different than what we were doing last class. It's just now we actually have to find a z-score, right? Well, before, when it's 0, 1, like it was last class, all you had to do is pretty much go right to the chart, all right? All right, any questions? All right. And again, I can see the chats. So if you don't want to ask, just open up the participants and send a chat, and then they'll pop up and I'll see your question as well. Or you can just ask. I'm fine either way. Do what?
I have a quick question.
Yep.
So the z-score is the negative 0.25 we got.
Yep.
Okay. Had to clear that.
Yep. Nope, perfect. Yep, that's step 2. So step 1, we draw. Step 2, we find our z-score, and that's why the formula has a cool z in it. So that when we actually solve that thing, we'll know our z-score, and then we can go to the table, which is step 3. All right. So sticking with the same problem. So I'll draw the picture up before I forget the numbers. Centered at 3.0, a deviation of 1.2. So now I want to know, what is the probability that a student has a GPA of 3.4 or higher. I'll put all of that in parentheses. So my event now is my 3.4, right? So if 3.0 is in the middle, 3.4 is about right there. And we color which way?
Right.
To the right now. So step 1 is complete. Now, step 2, find our z-score. So z equals, parentheses, 3.4 minus 3.0 all over 1.2.
I got 0.3 repeating.
I did as well. So 0.33. And remember, for its table, we only need 2 decimal places. So as long as we round to the second decimal place, we're okay. So we got 0.33. Then third step, we go to our table. So it is a positive this time. So we go to the positive side. And again, what you do, start with the first 2, find that in the left column, then find the last number in the top and line up your fingers. So 0.33. 6293. 0.6293. We should get that right. Very good. All right.
Wait.
Nope. Okay. Yeah. Good. Thank you.
Why did you put the 3.0? Like the 3, like in the middle right there, or like even like.
Because this is our mean. Remember. So this is our mean.
Yeah.
This is our x, and the z formula is x minus mu all over sigma. So I just put the numbers where they would go. So my x went there, my mean went there, and then my standard deviation went there.
Could you go back to like the first one? What was the probability that we were trying to find? Like, can you just show that if you can go back? I don't know if you can.
Yeah, I can. Yeah, these don't get erased as long as I don't close them. So here we were trying to find a GPA is less than 2.7.
So it doesn't include 2.7.
So yes. So one thing we haven't covered.
Because like when you first gave the scenario, it was a selected student at CMCC has a GPA of 2.7. So I'm just confused now. I guess.
Yeah, I should have put it in
myself.
No, I should have added the words or less. So I should have had those in there. And the reason is, let me answer that in 1 second. Because I forgot we didn't cover this in class yet because we didn't get to this before break.
Okay.
So, but I'll come back and explain the difference here in a minute. So 6.293, right? Now, what is the issue? My math is all correct, but there is a small issue. We have to do an extra step on this problem. Why?
Is this the one where you have to take the complement of it? No, that doesn't make sense.
Yes. Marissa, stop doubting yourself. You always give me the right answer, then you doubt yourself. Yes, we have to do the complement. Why?
The chart reads to the left.
Because the chart reads to the left. 0.6293 is over here. We want its opposite. We want the right. So if we ever want the opposite, we do the complement. So we do 1 minus 0.6293. So our final answer is 0.3707 or 37.07% chance. There was a 37.07% chance that a randomly selected student has a GPA of 3.4 or higher. So just to recap, because we colored to the right, we have to do an extra step, because anytime we take values out of the table, they are always to the left of your event. If you ever want to the right of your event, you must do the complement.
So basically that's if it says 3.4 or more instead of 3.4 or less.
Yep.
Okay.
Is this always going to be the case when it's a positive z-score?
No, it doesn't matter that it's a positive z-score. It matters
Or when
that
it's
it
colored to the right?
Correct.
Okay.
Yes. Every time it's colored to the right, this will have to happen. All right. So now to Shelby's, I think it was Shelby talking to me, his question about equals. All right, let's see if I can explain this visual over the internet better than I probably do in class. So our mean is 3.0. We have a standard deviation of 1.2. And if we go back to the question where I didn't write it perfect, I said 2.7, right? The way probabilities work, probabilities are the area under the curve, right? So when I shade this, I'm actually doing calculus. I am finding what we call the area, which in calculus means we're going to integrate, right? So probabilities and area are the same. That's what you're trying to find out. How much space is it taking up, right? And in the discrete world, chapter 5, right, it was easier because remember when we graphed ours in chapter 5, make that a 1/2. We just added the points together, right? And the reason we could do that is because it was discrete. Well, in the continuous world, we can't add, we have to integrate. And this is because it's continuous. Now, the easy way to prove this is through calculus. So that's why it's a little more challenging. But the probability that x equals 2.7 exactly is 0 in the continuous world. Because we're dealing with area under the curve, 2.7 is at this exact spot, which means it's not really taking up any area under the curve. So that's the calculus explanation. What I tried to do when we talk about this in class is when do you get exactly the number 2.7? Well, that's when you have 2.7 0, 0, 0, 0, 0, and I'll put a bar over it. Zeros go on forever, right? So in that case, if we do probability, there is only one number that is exactly 2.7 with zeros that go on forever. And how many numbers on their number line is infinite. And without getting into all crazy math of limits, basically 1 over a very, really large number is equal to 0. So there's the non-calculus way of trying to understand it. But the big takeaway from this whole thing of me rambling right now is when we're dealing with continuous, you cannot do equals because the probability is always going to be 0. So the big takeaway for you all, you will always color to the left or color to the right. It'll never be perfectly equal. Does that help explain things a little? If not, please just hit the I believe button that you can never do equals in continuous. And if you really, really want to know, whenever campus opens back up, come see me and we can do some calculus together and I'll show you why it really works. So, sorry, probably not the best answer, Shelby, there you're looking for, but in probability, we can't do equals for continuous functions is the simple answer. So it will always be less than, more than, at least, greater than, at most. It'll be just like very much like the wording in the chapter one test. I mean, not chapter one test, first test, where you just had to pay attention to the wording. But the wording you will not see is exactly.
Okay.
Okay. Good question. Sorry, I probably didn't explain it as well as I would like to. All right. So if we stick to our same problem of GPAs, now I can ask, what is the probability? I'm too close to the top, keeps messing up my writing. Probability of a randomly selected student has a GPA between I don't remember what our mean was anymore.
3.0.
3.0.
Thank you.
And our standard deviation was 1.
Okay, so has a GPA between 2.8 and 3.1 with a mean of 3.0 and a deviation of 1.2. All right. So first thing we do is draw a picture. 3.0, deviation of 1.2. This is 2.8. This is 3.1. And where do I color?
Between the two?
Between. So, because I have two events, I will have to find two z-scores. So z equals 2.8 minus 3.0 all over 1.2, put in my parentheses, and then z equals 3.1 minus 3.0 all over 1.2, put in my parentheses. 2.8 minus 3 over 1.2. Negative 0.17. And a positive 0.08. So here was my step 2. So now my step 3 is to go to my table. So I will start with my 0.8. Which gives me 0.5319. And then my negative 0.17, 0.1, you're right, 0.1, there we go, 7, 43.25. Everyone agree with me that's playing along?
Yep.
Okay, good. Now, we do have an extra step again. because they're not colored the right way. We've colored in between. So we're to the left of one number, but to the right of another. So we got to remember how this works. So I'll try to do this without screwing everything up here. When I found this z-score, I'll put a blue star by it. That is all the way to the left, right? So that is starting at my 3.1 and going to the left. And so you notice, because it goes all the way to the left, I went past the red line, right? Now, if I go with my other z-score I calculated, I'll put a red star by that one. That is everything to the left of 2.8. So if I take out that spot that is colored red and blue, that will leave me only the green piece left, correct?
Yes.
So to remove something means to subtract. So if I take my two probabilities and I subtract them, I will have my answer. Hopefully not run out of room here. 0.0994. So a 9.9% chance that a randomly selected student will have a GPA between 2.8 and 3.1. Let everybody think about that for a second and ask any questions they would like.
I think the math was wrong.
Can I type it?
0.0814.
0.0814.
We're subtracting those two. Yeah.
Check and make sure you didn't put a decimal in the wrong place, because they're 43 and 53 are about 10 apart. So I think mine's okay. It's about 53% minus 43%.
We just tried it again and it was the same thing.
Let me use my technology to make sure that I didn't screw this up, but I think I'm good. Normal. So I want to go 2.8 to a 3.1 with a mean of 3.0. Is no anyone?
Forget it.
Is it right?
Yes.
Okay.
I'm just in control of the microphone for two of us right now.
You're fine. I figured. All righty. So I'm happy you're asking questions, Ben. So it's good. At least I know someone's following along. All right. So we've done three different types now. We've done one color to the left, which we could do in 3 steps. We've done one color to the right, which we had to do an extra step. And we've colored one colored with a between, which we had to do an extra step.
Chris,
So,
can I ask a question?
you sure can.
The in between, are we always going to be subtracting for it? Or is
Yes.
there a word? Okay, cool. Okay, thank you.
Yep. Yeah, if you know the difference between the 3, the steps will never change. These are the steps. All right, let's look at the last case scenario like we did last class. So, sticking with our problem, what, I don't know, I always put my eraser on first. What is the probability? God dang it. I'm trying to save space, but every time I get near the top, it doesn't let me write. What is the probability? No, not probability. what is the GPA of a random student that is in the top 5%? We already did 5%. Let's do a different one. We did that last class. Top 10%. So, what is the GPA of a random student that is in the top 10%? So this one's a little different, but the steps are still very similar. Step 1, draw a picture. So I'm still centered at 3.0. I still have a deviation of 1.2. Now in this case, I don't know my event. I know my percentage. And remember, percentage is the colored region. So where is the top 10%? In the bottom, or in the left or the right?
Right?
Right.
It's in the right. So I know I am over here, and this is 0.10. What I'm looking for is, what is this number? That's what this question's asking us, right? So if I go to step 2, like we always do, that equals Z equals, this is usually my X, so I'm just going to put a question mark in here for now because that's what we're missing, minus 3.0 all over 1.2. And then if I go on to step 3, my Z score gives me my percentage. Well, in this case, I know my percentage is 10%. So if I work backwards, I can find my Z score, right? However, again, this is a tough problem. So if we follow this all the way to the end, I think this ties it all together and we got it. What is the problem though with my percentage?
It's 0.01. 0.1.
Not so much that. Where is it located?
And the chart.
Sorry about that. No, where is it colored here? To the right or the left?
Right.
Right. Before we can go to the chart, we have to be colored which way?
Left.
Left.
Left. So, am I looking for 10% or am I looking for?
You're looking for 90%.
That's exactly what I'm looking for. I am looking for a 90%. So I go to the chart and I need to find 0, 0, 0, 0. Because remember, this is inside because it is a percentage. It is not in the columns. It is inside. So I need to find 0.9000 in the chart. Has anyone found it yet? Because there's 2 possible answers.
0.8159.
0.8159, yeah.
Remember, we're not looking for the Z-score of 0.9. We're looking for 90% in all of those numbers. What you two just gave me, you went and found a Z-score of 0.90. I am looking for the probability of 0.9000 somewhere in all of those 4-digit numbers.
0.8997.
So we get a 0.8997 or a 0.9015, right? They're right next to each other because 0.90 is between those 2 numbers, right? So then if I find my Z-score that goes with these for 0.8997, that is what, 1.28? 1.28. This is my Z. And for the other one, it should just be 1.29. Now, the big question here, which one do we use?
You can use both.
Why?
Would you use the 8997?
Why?
One's counting for a little more, one's counting for a little less.
Perfect. So everyone is correct. It has answered me. So if Ben likes this one because it's the closest, perfect. All right. If you prefer this one because 0.8997 is a little bit to the left here, right? We're not actually at the 10%, so this is a little less accurate. However, if you go with the other number, you're actually past the 10%, so that's a little more accurate. So it's more half full or half empty type of person, right? I will take both answers because you see they're really not off that far, 1.28 and 1.29. But it really comes down to kind of what you're trying to do. There is no hard rule. You could, what we call in algebra, interpolate and find the exact number, but we're not going to get into all that for this class. So I would say just go with what you feel. If you want to be a little more cautious, maybe you pick 1.29. If you want to pick the one that's closest to your answer, then you pick 1.28. Both of them are fine. So I will go with 1.28 just because it's closest. So that means I take this value and I replace it with this Z. Now I have to do algebra because I have to solve for the unknown thing. We have to solve for our X. So to solve for X, to remember how to do algebra, you have to bring the 1.2 over, right? So here's our algebra. So I have to do 1.28 times 1.2 because it goes from the bottom to the top. And then this is a negative 3.0, so then I have to add 3.0 to it. So 1.28 times 1.2 plus 3.0 gives me 4.54. So something is, oh, right, because I doesn't know you can't go that far away. That is weird. I've never had this happen to me. Did I mess up my math somewhere?
Hey, Chris, I have a question. Is there, and I hate to be this person, is there any way you can like use a new board and do it out so I can see how it's supposed to be like?
Algebraically?
Yeah, that would be good.
Yep.
Thank you.
So 1.28 equals X minus a 3.0 all over 1.2, right? So to do algebra, I'm dividing by 1.2, so to get it onto the outside, you kind of have to do the opposite. So that means I have to multiply this side by 1.2, because then this 1.2 and this 1.2 cancel. Well, what I do to one side, I have to do to the other. So I have to multiply, not 2. I have to multiply this guy by 1.2, right? So if we do it in steps, 1.2, clear, 1.2 times 1.28 gives me a 1.536. Sorry, go back to black. Then that 1.2 on the other side is gone, so I have just an X minus 30. Now I gotta get X by itself, so I'm subtracting 30, so I do the opposite, so therefore I'm gonna add, not 30, sorry, 3.0. I'm gonna add a 3.0, and I add a 3.0, which gives me 4.536 equals X. So there's the algebra.
Thank you.
Yeah, no, that's a good question. I don't mind doing that at all. Now, the issue with all of this is me picking a horrible problem. But also it's a good way to show this, why we still have to learn statistics, because the math doesn't always make sense logically. So for our problem, to be in the top 10%, you have to have a GPA of 4.5, which we all know for being college students that you can't have a GPA of 4.5, right? So basically, to get in the top percent, if this was a real problem and we apply it back to the real world situation, you have to have a perfect 4.0 to be in the top 10% if these were our true GPAs. So that's why we still have to learn it, because the computer and the calculations are just going to follow rules of mathematics. We, as the statisticians, have to interpret the results. And since 4.5 doesn't make sense, because we can't have a higher than a GPA of 4.0, then we would basically, what we're doing with this analysis for, we would tell them, hey, well, the people that have a perfect 4.0 are the ones that are in the top 10% at the school. But that's how you work. That's the hardest of the problems, and that's the one of working backwards, where you know the percentage, but you have to work back to find the event that goes with that percentage. Any questions on 6.2?
None here.
All right, so 6.3. 6.3 is kind of proven that our sample statistics are good estimators for our thing. So if I build my table that we had at the very beginning of the semester, I'm going to run out of room, I know I am. So we had what? We had proportion. We had the mean. We had the variance. And then we had the standard deviation. I'll write down here. Try to stay on one board. And then we had sample size. Or not sample size, sorry. Size. This is the table I built for you on the very first day of class, and I said, this is the entire semester on this table, right? So then we had our population up here, and then our sample. And then we started putting in symbols, right? The population proportion is a P. The sample proportion was a P hat. The population mean is the mu. The sample mean was the X bar. The population variance was sigma squared. The sample variance was S squared. Population standard deviation is sigma. And the sample standard deviation is S. Population size is a capital N, and the sample size is a little n. These are the symbols you should have memorized by now. No more than the fact that we do them all the time, right? And if you can get this chart down and understand what these concepts are, the rest of the semester goes fairly well. If you're still really confused about these symbols, you need to spend the weekend while you're stuck in the house anyway and get them down, because they're going to be used a lot for the rest of the semester. Now what 6.3 is, so this is what I already gave you. 6.3 is this little piece right here. Biased or unbiased. And 6.3 proves all of this. This one is unbiased. This one is unbiased. This one is unbiased. And then this one is biased. And this is just a size, so it doesn't really mean anything. It's just how many people you're picking. Because we don't actually calculate, that's something we know. But these are the things we calculate, and they're unbiased. And basically what unbiased means is this can equal this, and this can equal this, and this can equal this, and this can be approximately this, right? So in 6.3, when you read it, it goes through and proves all of this mathematically. For me, I think the better way to prove all of this mathematically is to do dice roll. So hopefully most of you were able to find a dice. A die, I only need one. And what I need you to do is roll the die 10 times and calculate its mean. And I'm going to build a little chart so you give me your numbers. So we have 1, 2, 3. And this works really good in class. So you were my first attempt to see how well this works virtually.
My mean was 4.
Okay. So I have a 4.
Mine was also 4.
And if you don't want to talk, you can always chat it too. But I just need whoever's participating to do it. Give me some numbers so I can make my little graph for me, please.
2.4.
So 3. Say again, Ben.
2.4.
2.4. Okay. I just saw someone chat 3.8. Trying to make them the same size if I can. Okay. I 3.4. Okay. I got a 3.
4.3.
I got a 4.3. I got a 5.
I got 2.
I got a 2. I have a 3. I have a 4.
I got a 3.
I have another 3. I have a
4.
3.8 and a
2.
4. 8. A 2.
Mm-hmm.
Okay. All right. Do it again, please. And if you're still doing it the first time, you can still keep giving me numbers, but I like to try to get at least 2 numbers per person. I'm actually pretty happy with this. It's actually not going too bad virtually, in my opinion. My drawing skills, I could use some work, but the experiment is going okay. .7. Those are my 8, so the 7's right there. Okay.
I got a 5.3.
Oh, wow. All right.
Well, my son gave me a weird 7-sided die from his Sonic game.
3.1.
4.5.
2.9. 4.5. Okay.
3.4.
3.4.
2.7.
2.7. 5, 6, 7. Someone just text me a 1. 3.4. 3.6. I'm gonna check my chats now. I thought someone just said 1.
Yeah, they did.
All right. I mean, it can happen, so I'll take it.
2.
2. Make sure I got them all. Yep. Okay. Doing good. Close my chats. All right. Well, some people are finishing up. They're still doing it. Roll a die. So we're rolling a die. We did it 10 times, right? The probability of each side is 1/6. They are independent. You either get a number or not. No, sorry, no, it's not binomial, never mind. So almost binomial, but it's not quite binomial because of the fact it's not success or failure. So if I go back to chapter 5, this is my graph. Here's my P of X. Here is my X. This is my probability distribution function. All right, I see the 3.8, adding it to the chart, thank you. And X can be 1, 2, 3, 4, 5, 6. With a probability of 1/6. And there are my outcomes. And there is the graph of my probability distribution function from chapter 5. And in this case, they are discrete. So that the top graph is what rolling a die looks like according to the probability distribution function. My bottom graph here is what it looks like when we roll it 10 times and we calculate its sample mean. So this graph, if I label it, is X bar. Why is this a sample mean?
Because you're collecting your samples.
Yeah, okay, the samples. We did it 10 times and we found its mean, right? What does my bottom graph starting to look like?
Bar graph.
Histogram,
It is a histogram.
but a bell.
Shaped curve.
Oh. It's starting to take on a bell shape, right? So we've gone from a problem that basically almost looks like a flat line, but because it's discrete, we can't connect the dots. But if you look, I mean, if I could draw straight, that would help. But they kind of look like a straight line, right? But when we take the means of them and we calculate and plot them, it starts to look like a bell curve, right? This is what 6.3 is saying. And this takes us into 6.4, which we will call the central limit theorem, which is where we will start Monday's class, right? And if I had you all do this again and again and again, you would notice that this would start to look even more bell-shaped, and it would start to rise at the mean. And the mean, if you take this times this and this time, and you multiply all the numbers, the mean is 3.5. And that's going back to chapter 5. Remember, in chapter 5, to find the mean of a probability distribution function, you take the event and you multiply it by its probability. Take the event, multiply by its probability. Event, probability, event, probability, event, probability, event, probability, and then you add them. If you forgot that, look at test 1 and you'll see the problem where you had to do that. So if you actually take 1 times 1/6, 2 times 1/6, 3 times 1/6, 4 times 1/6, 5 times 1/6, 6 times 1/6, add them, you will get 3.5. So if we kept rolling the dice over and over again, this thing should spike at 3.5, according to the central limit theorem, right? So that's what 6.3 does. 6.3 basically proves this using mathematics. I think it is a much easier proof to see visually. If you open up my Excel, which is what I tried to do, but I could not get to work well on my computer, there is a tab that's called Dice Roll. And if you open it up and you click on that tab and then you hit F9 on your keyboard, it will rerun my simulation over and over again, and it should have a histogram, and that histogram will be bouncing all over the place every time you hit F9, and that histogram will look like a bell shape, right? So if we're in the classroom, I could show you, because I have much better Excel on campus than I do here at the house. I will try to figure out how to get it to work on my older computer here. I think I will use my coronavirus fund to go buy me a new Mac whenever the stores reopen, so I don't have to do this anymore. But that's the whole point of 6.3. This is to get this to prove that no matter what distribution you start with, if you take a sample and you calculate the mean and you do it over and over and over again, and you plot the means, the histogram of the means will be normally distributed always. That's the key takeaway from 6.3, right? So what it does in 6.3 is it kind of goes through and does the math to prove that for the proportion, for the mean, and for the variance, because those are all unbiased. The standard deviation is biased, and we know that, and there's some advanced algebra that I can do to prove that to you again once we get back on campus if you want to see it. But for now, I would hit the I believe button and just realize that out of all of the sample statistics, the standard deviation is the biased one. The other three are unbiased. Any questions on anything we've covered today?
None.